always started off this morning highlighting our project goals, right? To adapt corn-based cropping systems to climate change and to mitigate the impacts of corn-based cropping systems on climate change. And then Ray just took us through some strong links between climate change and greenhouse gas emissions. So now I'm going to switch to talking more about greenhouse gas emissions, how we inventory them, how we measure them from agricultural systems, what agricultural systems' contribution to greenhouse gas emissions is, what the mitigation potential is, and just some very broad strategies as to how we might mitigate greenhouse gas emissions from agricultural systems. So the EPA identifies about 17 greenhouse gases, and they all have a different capacity to trap heat in the atmosphere. So Ray talked about how different gases trap heat in the atmosphere. On a mass basis, each one traps a different mass of heat in the atmosphere. So what we use to standardize this is a measure called global warming potential. And this measure relates on a mass basis how much heat trapping capacity different greenhouse gases have. So, for example, 1 metric ton of methane, CH4, has about the capacity it's about similar to the heat trapping capacity of 21 metric tons of CO2. Nitrous oxide, it would be about 310. So we standardize these with this measure called global warming potential, and those are the data that I'm going to show you today, things that have standardized for the mass differences and the heating potentials of these greenhouse gases. So there's 2 important points from this slide in addition to that. 2 important points, the reason I boxed those 3 gases at the top, CO2, carbon dioxide, CH4, methane, and N2O, nitrous oxide. The first is that all those gases are biogenic greenhouse gases. They're produced and consumed by biological systems, in contrast to the others, which all have industrial syntheses. The other reason is those 3 biogenic greenhouse gases account for about 97% or more of the total anthropogenic greenhouse gas emissions globally. So the major forces behind anthropogenic greenhouse gas emissions are biogenic greenhouse gases. We know agricultural systems are biological systems. So the next logical question is, what's agriculture's contribution to the production of these greenhouse gases? So, like Ray, I'm going to give you guys a quiz. What do you think agriculture's contribution is? Is it small, large, moderate? Well, like any good professor, it's a trick question, right? The answer is it depends. At the US scale, greenhouse agriculture as a sector accounts for about 6.3% of our total global warming potential. So once we've corrected for the mass basis of those different greenhouse gases. At the global scale, it's at least double that, and folks often cite it at 30%. When you hear that 30% number, they're lumping together forestry and agriculture. And the reason for that is largely the forestry is land clearing for cropping systems, right? So it really is agriculture, cropping systems, agriculture, and nature. But there's a couple important things to notice on this slide. And in the US, where we're working, of course, forestry isn't included on there. Forestry is a net sink. We've already converted all our cropland in the United States, largely. The other thing to notice is, even regardless of that lack of forestry in the United States, our proportional greenhouse gas emissions, the agriculture sector's proportion is far lower than the globals, right? 6.3 versus 13.5%. That's really an indicator of the high production efficiency of agricultural systems in the US, and that's a topic I'm going to come back to later in the talk. Our systems are highly efficient, we have a lot of high production, and that results in a lower proportion of greenhouse gas emissions, one of several reasons. So let's take a closer look at that 6.3%. So almost half of that is nitrous oxide emissions from cropping systems, right? From the fertilizer we add to cropping systems. The other half of that is largely from livestock production systems. So the nitrous oxide is a big important piece of this. The other 2 things to notice on this slide, thinking about cropping systems, the corn-based systems that we work in, you don't see CO2 on there, and the reason for that is the EPA and evidence supports this, that most of the CO2 flux is in equilibrium. So soil organic carbon stores, where that CO2 is stored in cropping systems, is about in net equilibrium. It's not changing very much. And then methane, of course, isn't included because it's a very minor sink for greenhouse gases in cropping systems. They take up methane. So here's how we measure these in the field in practical terms. So CO2 and nitrous oxide, we literally put a lid over the soil surface, and for nitrous oxide, we measure the net production of it over a given amount of time, and we scale that to a mass per area or other units. CH4, we measure the reduction in concentrations over time, scale that back to a mass. For CO2, it's much different. We can't measure CO2 fluxes over the soil surface because they're constantly going in from plants, and then they're coming back out, both from those same plants and from heterotrophs in the soil as well. So you can't get a good measure by putting a lid on the soil surface. So rather what we do is we take soil cores, and I think Sasha will be talking about that more later. And those soil cores, they integrate other fluxes too, like erosion, dissolved organic carbon leaching. So it's not just the CO2, but it's included in those. So here's an old example of what those data look like from a corn cap site, actually, one of the Michigan State sites. So what you're looking at here is a comparison of the global warming potential of two different systems. So those scaled fluxes of CO2, CH4, and N2O. And what you see is in a conventional system, consistent with that EPA assumption, remember there was no CO2 on that slide, that the net carbon balance is in equilibrium. And what you also see is nitrous oxide accounts for far greater than 90% of the total global warming potential from that conventional site. In the lower input legume cover system, you see that that system's a net carbon sink, right? So soil organic carbon is increasing through enhanced CO2 uptake by plants in that system, and lower decomposition perhaps. But again, nitrous oxide is the biggest contributor to global warming potential from that system. So I want to point out here, this is an old study, over 10 years old now, and you'll see the units at the top, CO2 equivalents in a mass per hectare, so really a global warming potential per area. We don't really think about greenhouse gas emissions in agricultural cropping systems in those units so much anymore. We think about them more in terms of units production, so energy production in terms of the crop, protein production, things like that, right? So here you see the lower global warming potential of the low input legume cover site, but in reality that may be far higher on a production basis of agricultural goods. So what's the potential for mitigation? This is a figure from the UN's 2007 report. And what we see here are numbers in metric tons of CO2 equivalents, global warming potential, the technical potential to mitigate greenhouse gases in the absence of cost factors, right? And what I want to point out here in the red circles is the U.S. is relatively low compared to some other areas of the world, South America, China, India. Again, this gets back to that production efficiency that I mentioned earlier. We're producing relatively efficiently in the United States compared to other areas in the world, and that shows up in our technical mitigation potential. And it's really testament to much of the extension work that goes on that many of you are involved in. We're not over-applying fertilizers. We have high production. Those are all things that lower our greenhouse gas footprint, and I'll continue on to talk about here in another slide. But again, more evidence of the fact that high production efficiency is a good thing for lowering our global warming potential and greenhouse gas emissions. Here you see cropland, here is the economic potential for mitigation, right, across all different strategies in agricultural systems, cropping systems. And what we see is cropland management is relatively insensitive to the price or potential price of greenhouse gases, right? And the reason for that, one of the reasons for that is that high production efficiency and low greenhouse gas emissions per unit agricultural product are really consistent goals. Unlike things like restoring soils that would be much more sensitive to costs. So here's just another, I want to finish with a couple slides here, one highlighting this relationship between high production efficiency, high yields, and low greenhouse gas potential. So on the left here, we see You know, we know our yields increase to a point with nitrogen fertilizer, and then we get no response in yield anymore. Being at that high point on the yield curve without going beyond it with adding fertilizer is really important to maintaining our soil organic carbon stocks. In fact, Rattan's been one of the biggest proponents of this concept, I think, in the world, that maintaining high yields is necessary to maintain our soil organic carbon stocks and minimize that component of the global warming potential of agricultural systems. Similarly, we don't want to go beyond that yield curve point, though, with nitrogen fertilizers, because that's when nitrous oxide emissions start to skyrocket from agricultural systems per unit product. So really the take-home messages here are greenhouse gases that contribute to global warming potential. The main contributors are all biogenic, right? So they're consumed and produced by biological processes, agricultural systems. Cropland management certainly has some economic potential to mitigate anthropogenic greenhouse gas production. And when we express the global warming potential or the greenhouse gas footprint of agricultural systems, really it's best to express it on a per unit of products more so than per unit area, and high yield and efficient nitrogen use are the broad keys to lowering that global warming potential. Thanks.